Hello world! Welcome to this series where I'll be taking on every single LeetCode daily problem for January 2025. This isn't just about my personal growth, it's also here to help anyone who loves problem solving learn and grow together. In each video, I'll walk you through my thought process step by step, so you can see exactly how I approach different kinds of problems. And of course, I'd love to hear your thoughts, suggestions, or even alternative solutions in the comments. Your feedback really helps me improve. Alright, let's get started. On January 1st we got a simple problem. All I've to do is iterate every index I and calculate the number of 0 on the left side and the number of 1 on the right side to get the maximum value. On January 2nd, I got an interesting question which requires to calculate for each query. Always keep this in mind. Whenever a problem involves range queries, your first thought should be about prefix sums or suffix operations. And if the problem goes further, think about advanced tools like segment trees or binary index trees, because all of these data structures are specifically designed to handle range queries efficiently. So this problem basically comes down to calculating prefix sums, but only for the strings that start and end with a vowel. Then, to answer a query, we just take the difference between the prefix sums at the right and left indices. On the next day, we tackled a problem that was practically made for prefix sums. The last element of the prefix array gives us the sum of the entire array, and by subtracting the prefix at index I, we immediately get the sum of the subarray from I plus 1 to the end. The next problem asks us to count unique palindromic subsequences of length 3. So first, let's imagine what a length 3 palindrome looks like. And second, what attributes a subsequence has can help us. A palindrome of length 3 is just a string that starts and ends with the same letter, doesn't matter what's in the middle. And since a subsequence doesn't need to be continuous, we can simply take the first and last occurrence of each letter, then count how many different letters fall in between to get our answer. The next problem asks us to shift letters based on a series of commands. Right away, two things came to my mind. How to handle shifting in both alphabetical and reverse order. How to figure out the final letter after all the shifts. To start, we can use modulo 26 to handle circular shifting, since there are 26 letters in the English alphabet. If we treat a forward shift as +1 and a backward shift as -1, then we can apply a segment tree to perform range updates and figure out the final letters after all the shifts. I'll leave my segment tree template in the description, so we don't need to dive into the full implementation here. The idea is simple. We collect all the shifts and calculate the total delta for each range. Then, for every letter, we just apply that delta and take modulo 26 to get the final shifted letter. On the next day, this problem asks us, for each box, how many moves are needed to bring all the balls into it, if we can only move them one step at a time. The trick is to look at it from both directions. From the left, we keep track of how many balls we've seen so far, and how many steps they would need to reach the current box. From the right, we do the exact same thing. Finally, for each index, the answer is just the sum of the moves from the left side and the right side. This trick works by iterating forwards and backwards to accumulate the steps from both the left and the right. In other words, we keep track of how many balls we've seen so far and add their contribution to the total moves as we go. On January 7th, we got another easy problem. A basic string check is enough. And keep in mind, in Python, KMP is used under the hood for the in operator, so the time complexity is guaranteed to be efficient. Two easy problems in a row. This one we can simply use the built-in functions, starts with and ends with. After 3 days of easy problems, I finally got a medium one on January 10th. Even though it's labeled medium, the problem really just asks, which words in the first array can serve as supersets for all the words in the second array. The trick is to build an overall counter, tracking the maximum number of each letter needed across all of words 2. Then, for every word in words 1, we just check if it meets those requirements. On the next day, we meet palindrome again. In this problem we are asked if a string can be divided into k groups of palindrome. I always start by asking, how can I tell if a palindrome can be formed? The key idea is that in a palindrome, at most one letter can appear an odd number of times. If more than one letter does, we can't form a palindrome. So all we really need to check is whether the number of letters with odd counts is less than or equal to k. If that's true, then we can definitely construct k groups of non-empty palindromic strings. Next, we got one of my favorite types of problems, checking parentheses. The trick here is to scan twice. From the left, we treat every opening parenthesis or unlockable position as a resource we can use, and make sure we never run out when we see closing parenthesis. From the right, we do the same but flipped, treating closing parenthesis or unlockable positions as resources against opening parenthesis. If both scans never go negative, then the string can be made valid. On January 13th, we got an iconic sliding window problem. Even though the description talks about a delete operation, we don't actually need to simulate it with a stack. After looking closer, we can see that whenever the same letter appears 3 times in a row, it collapses into a single letter. So we can solve it with a sliding window of size 2, and in the end, just count the remaining letters to get the final string length. On January 14th, I got a really interesting problem. We could solve it easily with a set, but I wanted to take this chance to practice some bit manipulation instead. Now, the problem specifically tells us that both arrays are permutations. That's important, because each number from 1 to n appears exactly once, we never have to worry about duplicates. Without this guarantee, our bit mask method could accidentally count the same element multiple times. With that in mind, we use 2 bit masks, one for A and one for B. Whenever we see a number, we flip on its bit in the corresponding mask. If that number has already appeared in the other mask, we increase the common count. This way, we only need constant per step to check and update. The next one is a practical bit manipulation problem. We need to find a number x such that x has the same number of set bits as the second input, and the value of XOR or the first input is minimized. XOR works like a difference detector. Each bit contributes to the final value only if the two numbers differ at that position. So, to minimize XOR, our best strategy is to make as many high-value bits identical as possible, since mismatches in higher positions contribute much more to the total value. That's why we first align the set bits of our result with the set bits of num1 from the top down. This keeps the most significant positions the same. And once we've matched as much as we can, we fill any remaining set bits in the lower positions, where mismatches have the smallest impact. This way, we guarantee the exact number of set bits required, while making the XOR value as small as possible. The next problem asks for the XOR value of all pairings between nums1 and nums2. This highlights one of the most iconic properties of XOR. If a number is XORed an even number of times, it cancels out to 0. If it's XORed an odd number of times, it stays. A good way to see this is to write out all the XOR operations and check whether each number appears an even or odd number of times. Coming back to this problem, if one array has even length, then after pairing with the other array, its contribution cancels out to 0. That means we don't need to explicitly iterate over it. The next day we finally got our first hard problem. But don't let this one intimidate you. This problem is really just a shortest path search on a grid. Each cell points in one of 4 directions, and following that arrow costs nothing. But if we want to move against it, we pay a cost of 1. So we can solve it with a BFS. When the direction matches the arrow, the cost is 0, so we push that state to the front of the queue with append left. When the direction doesn't match, the cost is 1, so we push it to the back with append. By always expanding the zero cost moves first, we guarantee that we're exploring paths in order of increasing cost, just like Dijkstra's algorithm, but much simpler and faster here. In the end, the distance matrix tells us the minimum cost to reach the bottom right corner. We got too hard in a row. This problem is the 2D version of trapping rainwater. The key idea is that the amount of water trapped inside is always limited by the lowest boundary around it. So we start from the outer boundary and push all border cells into a minute heap. From there, we expand inward, always taking the lowest current wall. This ensures we never overestimate the water level. Whenever we move to a neighbor, if its height is lower than our current water level, that difference is the amount of water trapped there. Otherwise, it just becomes part of the boundary. By gradually moving from the lowest walls inward, we correctly accumulate the trapped water across the whole grid. The next problem is a perfect example of dealing with unique numbers. Whenever a problem mentions that numbers are unique or appear only once, we can treat each number as a key in a hash map. With that in mind, we map every value in the matrix to its row and column. Then, as we iterate through the input array, we update counters for the corresponding row and column. The moment a row counter reaches the total number of columns, or a column counter reaches the total number of rows, we know that row or column is completely painted, and we return the index. On the next we got a game theory-like problem. Imagine the first player moves along the top row, then at some index drops down to the bottom row. At that turning point, everything left on the top row is blocked, and everything collected on the bottom row to the left is also blocked. So for the second player, their maximum possible score at that index is the larger of two options. 1. The remaining sum on the top row to the right, or 2. The collected sum on the bottom row to the left. Since the second player always plays optimally, we take the max of these two. And because the first player wants to minimize the second player's score, we then take the minute across all turning points. On the next day we got another medium. The key idea is that every land cell's height is its distance to the nearest water. If we only scan once, say from top left to bottom right, each cell only gets updated based on the top and left neighbors. But the nearest water might actually be on the bottom or right. That's why we need a second pass, scanning from bottom right back to top left, so each cell also considers bottom and right neighbors. With 2 passes, every cell sees all 4 directions, ensuring the minimum distance is correct. On the next day we got an easier problem. The task is simply to count servers that can communicate, which means there must be at least one other server in the same row or column. In my solution, I reused a BFS-like template with directions and a queue. The only twist is that instead of just checking neighbors, we scan all the way to the boundary in each direction to find connected servers. On the next we got a super interesting problem and requires a more advanced technique. To me, topological sort on the reverse graph came in my mind at first. We start with nodes that have no outgoing edges in the original graph, because they are obviously safe. By reversing the edges, we can peel the graph backwards. Each time a parent node loses all its outgoing edges, it also becomes safe. This way, safety propagates layer by layer until all eventual safe nodes are found. The next problem may look intimidating, but it can be solved by grouping numbers into clusters, where any 2 numbers in the same cluster differ by at most the limit. Inside each cluster, we can freely reorder to get the smallest possible result. The interesting part is how we find which cluster each original number belongs to. Here I used binary search to locate the right cluster, essentially finding the upper bound of where this number could move. That's my key takeaway about binary search. It's not just about equality, it's about finding the farthest position a value can go while still satisfying the condition. The next problem is by far the hardest in my opinion. This problem is all about invitations following the favorite links, which naturally forms directed cycles and chains feeding into them. The first thing to realize is the importance of tree depth. Whenever a cycle exists, the chains leading into that cycle decide how many extra people can be included. That's why we need to keep track of how deep each node's path is. Then we have to distinguish between two cases. 1. Two-node cycles. These are special because both people can attend together, and we can also attach the longest incoming chains on each side. 2. Cycles larger than 2. Here, only the cycle itself counts, since adding external chains would break the structure. The final answer is whichever is bigger, the sum of all contributions from 2 cycles with their chains, or the size of the largest cycle longer than 2. The next problem is fairly straightforward. Since we only need to check whether course U is a prerequisite of course V, a union-find structure is already powerful enough to group related courses. The real key is how to represent these prerequisite relations. For that, I built an adjacency graph and used DFS to trace whether one course can eventually reach another. The next problem is very direct as well. We just need to find the maximum number of fish in any connected area of the grid. The approach is to run a DFS starting from every fishing spot. Each DFS explores all reachable cells, adds up the fish, and marks them as visited. By repeating this for every unvisited spot, we cover the whole grid and keep track of the largest total. The next problem is a classic use of union find. I would love to bring up some of the optimizations here. 1. Path compression, and 2. Union by rank. With path compression, every time we call find, we flatten the tree by pointing nodes directly to their root. That way, future lookups are much faster. With union by rank, we always attach the smaller tree under the larger one. This keeps the structure shallow and avoids building long chains. Most of time we can achieve promising performance with these techniques when doing LeetCode problems. So, back to the problem, if the two nodes already share the same root, we've found the redundant connection. The next problem is really hard to understand at first glance, but we can think of LeetCode problem number 785, is graph bipartite. Think of the graph as people standing in rows. If two people are connected, they have to stand in neighboring rows. So the first step is to check if this is even possible. If we ever find a connection that tries to link people within the same row, or rows that are too far apart, then the setup is impossible, that's an odd cycle. If it's possible, then the question becomes, how tall can each group be? For every connected chunk of the graph, we measure the maximum number of rows we can stack while still following the rules. Finally, we just add up these numbers across all components to get the answer. Finally, we are having the last problem of the month. The challenge here is that we can flip one water cell into land, and we want to know the largest island size we can create. The trick is to first run a DFS and give every existing island a unique ID. Along the way, we also record its area. Why do this? Because when we later consider flipping a water cell, that cell might touch multiple islands. By looking at their unique IDs, we can sum their areas without double counting the same island twice. Finally, we just try every water cell, add up the distinct neighboring islands plus 1 for the flipped cell, and track the maximum. And that's it for today's video. I really enjoyed this one, I hope you do as well. If you like this video, don't forget to hit the like button, subscribe to the channel, and share it with your friends. Let's keep learning together. I will see you in the next one.